Welcome back friends for another lecture on quantum field theory and quantum entanglement. So today we'll continue our discussion. So far what we have covered is quantization of the scalar fields, we have covered about interaction picture, we have taken we have done the Wick's theorem. Today I will revise a little bit over the Wick's theorem and then we will try to do some before going to the formal formal process of calculating the S matrix elements essentially. So we already mentioned about the S matrix. There are certain property, there is certain S matrix formal aspect of the S matrix calculations which is called the LSG reduction formula. Before mentioning that, I would like to do some sort of a algorithmic way of introducing how to calculate simple S matrix elements essentially. Today we will just do some couple of examples with the scalar fields which we have seen, and then we will continue because we will revise these things, and then of course that way we will also have some confidence that what we have done so far, learned so far, and then we will move to more formal aspects essentially. So welcome back again to this lectures on quantum field theory and so let us look at a simple process. So far we have been dealing only with scalar fields. Essentially we looked at the first interacting picture, and towards hopefully the end of the class we will look at the second set of interaction pictures essentially. So during the interaction picture we introduced the so called the S matrix. So the S matrix is essentially which takes all the in states to the final states, or the I states to the F states, which we defined to be F S I. So this has to be a unitary evolution which we have looked at. Essentially this has to be a unitary evolution which takes all the initial states to the final states of the eigenstates essentially. So the initial states and the final states are the eigenstates of the free theory, and the S matrix is the unitary evolution which we do the Dyson series which we have seen essentially through S calculated is the Dyson series in the interaction picture. I and F are free states, or let me put it in more eigenfunctions of the free Hamiltonian. Or the free Lagrangian or something. Okay, it is the same thing essentially, and then we wrote this down essentially in terms of simple examples of meson decay and so on. So we wrote some examples. So along the way we encountered the Wick's theorem essentially, which tells you that all the time order products have to be converted into normal order products. They are related to the normal order products, and so this is the basic idea that all the time order products are always normal order products essentially. So that is the Wick's theorem, and plus the propagators, that is a basic idea. So which in the series, which in the basic series will give you the in the basic Dyson series at the lowest level, in the coupling constant gives you the interaction picture. Today what we will do is the algorithmic picture of how to calculate a simple process essentially from a free field theory point of view essentially. So, we will start with an interaction which is Phi 4 or which is like a Phi 4 theory essentially. So, we will start with a Clyde-Gordon field. The Phi 4 is an interaction, very important interaction theory, and we will see some properties of it later on, but right now we will look at simple examples in which how two scalars can interact with each other essentially, that is the basic idea. So, so Phi 4 theory. So, we will write the Lagrangian. So, with the V of phi is the L interaction part or the interaction Lagrangian, which is nothing but so lambda phi dag of phi whole square. Okay. This is your Phi 4 theory. Okay. So, this phi is a complex field. Let us consider so it is a complex field, and so this has phi dag of phi whole square. So, this is a 5 to the power of 4. So, there are 4 real phi, phi has both real and complex imaginary components essentially. Now, to make it okay, in the real case, if phi is real, this Lagrangian just becomes okay. So, this just becomes, and these are the symmetry factors which will appear, which we will which will appear. Okay, we should know which these are the symmetry factors which takes care of all the meaning double counting and triple counting and various aspects about this essentially. So, when you take this Lagrangian and the L interaction is nothing but H interaction is nothing but your lambda by 4 factorial phi 4 phi to the power 4 essentially. So, now, so what are the wave functions in this? Now, the way to let us try to calculate a simple self interaction. Okay. Now, we want to use this Lagrangian. Now, this looks like a toy Lagrangian. Now, what is a phi essentially? Phi is like a scalar field, meaning what are scalar field means spin 0 particles. What are the spin 0 particles which we know? So, which we know, what are the, are there any examples, any real life examples? So, yes, there are examples essentially. So, the mesons scalar, okay, let me put it, the scalar mesons are such examples. And if you say for example pi plus minus can be written as a complex scalar field. Okay. So, pions, scalar mesons which are like pions, okay, charged pions So, pi plus and minus will be represented by a charge scalar field. Similarly, you can also have real scalar fields essentially. Okay, examples are in real life, real scalar fields h. Okay, before going to h, let me just say pi 0, okay, is represented by a pi which is a real scalar field. Let me here I should put a star and this thing such that to denote it as a complex scalar field essentially. Okay. So, if pions typically, okay, they are charged pions are charged, they have some interactions essentially like electromagnetic interactions and so on. So, in addition they can also have self interactions. Similarly, real scalar fields pi 0 can also have self interactions due to some QCD like interactions or something. The other example in which there exists in real life a real scalar field with exactly very similar kind of interactions is a Higgs field of the standard model. Okay. It has exactly the same kind of interactions, meaning 5 self interactions like this essentially. It is a real, okay, in yeah. So, it has exactly this kind of interactions. In fact, yeah, it has more than that essentially, but let us say that it has self interactions of this type. Now, a particle can have many interactions simultaneously. Say for example, charged pions could have self interactions, it could have electromagnetic interactions, and a real scalar field could have self interactions or many other interactions which have some, okay, other interactions. But as of when we are calculating certain thing, we take one thing at a time in an S matrix essentially. We consider one interaction at a time in a perturbation theory. So, in quantum field theory we take one interaction at a time at one order in coupling essentially, one interaction at a time at one order in coupling, one kind of let me not say order, let me not say first order, we will do it order by order essentially. In later classes we will do some, most of this course we will not do higher orders, order by order in perturbation theory. Okay, one kind of an interaction. So, we take only one particular interaction. Say if we are dealing with self interactions, we will only deal with self interactions in the S matrix and look at process. Okay. So, to be more simpler, let us start looking at simple examples. Okay, involve decays for example. So, if there is a pion, it can decay into 2 photons, okay, or 2 electrons or 2 muons. So, this is a process one can try to compute essentially. So, in which there is a scalar field, real scalar field, okay, which decays into 2 Dirac fields, which we will see later essentially, fermions essentially, or 2 gauge bosons, photons are 2 photons. Okay. So, these are simple decays which we can deal with easily. So, these are 1 particle decaying to 2 particles essentially. These are the simplest examples we can think of. So, in which one particle decays into 2 particles essentially. So, it could be a pion decaying into 2 photons, 2 electrons, 2 muons, and so on. So this could be, to be more accurate, we should put mu plus mu minus and everything essentially. Now, if you, then you can have some other simple process which are undergo in the name scattering. So in this case, so in this case, you can think of simple classes of scatterings which are called 2 to 2 process. So 2 to 2 process means that there are 2 incoming particles in the in states, essentially I contains 2 particles, say for example particle 1 and particle 2, and they scatter, and these are the initial states, and the final states are particles 3 and 4 or even 1 and 2 or so on, so essentially. So simplest examples would be, say for example the particle itself. For example, with the interaction examples which we are looking at, you can have 2 pi's or 2 scalar particles. Let us not call them any names as of now, it could be Higgs, it could be pions or something. So 2 pions or 2 pi's coming in as in states, and they go as out states, they themselves, because you only have one particle in your theory and it has self interactions essentially. So how do you deal with this kind of a scattering process essentially? This is called 2 to 2 scattering. So other examples, if you have fermions, say for example E plus E minus going into mu plus mu minus, or E plus E minus going into fermions, or it could go into photons and so on. So you can have Compton scattering, Rutherford scattering, Compton scattering, and various other examples which you can think about essentially. So when you are dealing with scatterings of 2 to 2, okay, there is some very important set of kinematic observables, kinematic choices which we use. These are called Mandelstam variables essentially. So what does Mandelstam variables tells you that? Now in a completely quantum mechanical picture, you will not know, what you are seeing is that there are 2 incoming particles and then there are 2 outgoing particles essentially. So each one comes with a momentum P1, P2, and the outgoing ones goes with a momentum P3, P4. So these are one's final states. So let me call this the dark ones. Okay, these are your final states and these are your initial states. Okay. So the green ones are incoming states and the yellow ones are your outgoing states. Now remember, these are functions of free particle systems essentially. Particle, okay, these are essentially free particles. So they are eigenfunctions of the free Lagrangian essentially. Now here the interaction happens, but independent of the interaction, in a relativistically covariant way essentially, how many kinds of momentum exchanges can happen is very clear, because it is a 2 to 2 process. This is a 2 to 2 process. So in a 2 to 2 process, you cannot, this is one of we will be dealing most of the time in this first course on quantum field theory only 2 to 2 process essentially. So, and then we will comment about other things, other cases. So, in this case, how many kinds of momentum exchange can happen? So, what are the all possible kinds of momentum exchange which can happen? So, these because you cannot tell in a quantum mechanical picture what is the momentum exchange which could happen. So, these could be when the two momenta align with each other. So, these particles combine together in a scattering process such that the momentums add with each other. So, that is called an S variable. So, that is P1 plus P2 whole square. That is one possibility. Okay. So, that is called the S variable. The second one is T, that is called P2 minus P1 whole square, P4 minus P3 whole square, and the third one is U. So, in the first case essentially when they scatter these particles essentially their momentum are so aligned that they add up with each other. Okay, they add up with each other and the scattering happens essentially. In the second case, the momentums only the difference in the momentum plays a role essentially. The only possibility is that the difference between the two momenta really makes a difference, will play a role in the scattering. So, they are sort of grazingly scattering with each other, and this is given by P2 minus P1 essentially the difference in the momenta, and so this so on so essentially. In the third case you can have P3 minus P1. There are two kinds of differences you can have which in the world differences you can have. This is purely for momentum, all of them are for, this is purely kinematics essentially, nothing to do with the kind of interaction, whether the interaction is strongly interacting, weakly interacting, whether it is self interactions, QED or anything. All 2 to 2 process will have the same kinematic variables which are can be written in terms of this S, T, U or parameters. So, which are the S, T, U parameter. Now, this gives you a fantastic understanding, meaning a way of understanding the scattering process essentially, as we will see in the examples which we will see essentially. So, and one interesting thing is they are not independent. These kinematic variables S, T, U are not independent, and as you can see S plus T plus U is equal to 4m square, assuming for all masses equal. That means all of the masses are m. Say for example E plus E minus going to E plus E minus example essentially. So, the masses are all the same. So, in this case essentially you have this. So, but this gives you one of the first nice way of understanding all possible scatterings which you can have in a given system essentially. Okay. So, now we have seen the decay essentially, we have seen the decays examples essentially. So, we can see the same thing for the scattering essentially. Now, what we can try to do, okay. So, in a given process the energy and momentum should be conserved. Secondly, the strength of the process also depends upon the interaction strength essentially, which is given by the H interaction, okay, when you are calculating the scattering cross section essentially. So we said we will do the Phi Four theory. So one of the algorithmic way is by calculating something called the Feynman diagrams. So what are these Feynman diagrams essentially? So when we did the weak interactions, essentially we saw that the weak interaction, Wick's theorem tells you that you can write everything in terms of Wick's theorem tells you that you can write everything in terms of all the time order product is in terms of all the propagators. A more general form of the Wick's theorem is time order product of phi 1 to phi n is equal to normal order product of phi 1 to phi n plus all possible contractions. So what are these contractions essentially? Contractions are like so what we have seen earlier, we have seen time order product of say phi of x, phi of dagger of y is equal to phi of x, phi dagger of y normal product plus delta f x minus y. So this is what we said, this is all this is nothing but your Feynman propagator. Earlier we have seen this thing. So we can define, okay, this is nothing but a contraction. The propagator is exactly like a contraction essentially. String of operators which we replace it with a Feynman propagator, so which we have said this is contraction. Define contraction as a pair of fields in a string of operators say something like phi of x1, phi of xn to mean replacing them those operators with Feynman propagators leaving other operators untouched. In other words, what we are saying essentially is that, so for two fields you have this nice picture that a time order product of phi x phi y, maybe I should put it this in the brackets, is equal to normal order product of phi x, okay, phi x phi dagger y, phi x dagger plus this thing. This is nothing but your contraction, essentially this delta f phi of x. But if you have multiple fields, the reason why we need multiple fields because we are dealing with Phi Four theory. Okay, so if we are dealing with Phi Four theory, what we need to do is that we have to write down all possible contractions. That means that you can have phi 1, phi 2 contracted plus all other operators untouched, phi 2, phi 3 contracted, all other operators untouched, and so on, so essentially. So, for example, the main thing which we need right now is the Phi Four theory. So, for n is equal to 4, what will it look like? Time ordered product of phi of x1, phi of x2, phi of x3, phi of x4 is equal to normal order product of phi of x1, phi of x2, phi of x3, phi of x4 plus, think of all possible contractors, okay, contractions essentially. So, you have phi 1 of x1, phi of x2 contracted, which I will put the denotation this way, and other two field phi of x3, phi of x4 normal ordered, okay, plus phi 2, phi 3, okay, let me write it down explicitly, okay, very similar terms, phi of x2, phi of x3, phi of x1, phi of x4 normal order, until this series continues, until you have all contractions phi of x1, phi of x4 contraction, phi of x2, phi of x3 contractions. Okay. So, you can have two contractions also at a time. So, this is like the general definition of generalization of the Wick's theorem. So, the basic idea is that you can write any time order product in terms of phi of x1, phi of x2 normal order plus all possible contractions. So, this contraction is nothing but replacing it by a Feynman propagator essentially. That is the basic idea, that contraction is nothing but a Feynman propagator while keeping the other fields which are in normal order. Essentially you do not touch the other two fields. So, you take all possible such combinations. So, all possible such combinations and you continue it by taking two contractions at a time essentially, taking two possible contractions at a time. And okay, this is a theorem, and this theorem goes by the name as a Wick's theorem essentially. So, this is the so this is well known and everything essentially, and there is a proof for this, and so you can actually do the proof for this, and then now we okay, and now we can use this Wick's theorem to get the expressions for the scattering cross sections essentially, for the Wick's theorem essentially, and then we will go to more formal process. So, yeah, so what I will do is I will stop here. So, this is the generalization of the Wick's theorem, and now we will start from here in the next class, okay, and I will apply it, say for example for nucleon scattering or nucleon decay, and then we will see how this leads to a simple algorithmic picture like Feynman diagrams, and then let us try to calculate one simple process, and that gives you some idea about how this entire field theory leads to some simple algorithmic rules which are called the Feynman rules, and leads to some simple algorithmic picture which is like Feynman rules, where you can calculate process at in principle now even at any order in perturbation theory essentially. Okay. So, let me stop here. So, what we have learned today is that we have learned that how to calculate, we started again redoing the entire scattering theory, the meaning S matrix approach and so on, so, and then we started looking at simple examples, and then we looked at the Mandelstam variables, and we started looking at coming towards the Feynman diagrams. Before that we looked at something called the Wick's theorem. I did not yet reach the Feynman diagrams, and so once we do that Feynman diagram, finish the Feynman diagrams, Wick's theorem, which the most general form for the earlier Wick's theorem we only did for 2 fields, now we are doing it for n fields, and then we saw that it is all possible contractions. It is just instead of one Feynman propagator you will have multiple Feynman propagators and all possible contractions, and this is sufficient for us to understand Feynman theory, Phi Four theory, and with this we can start building Feynman diagrams and calculate a simple process to phi phi to phi phi scattering cross section and so on. So, okay. Let me stop here and then we will come to phi phi to phi phi scattering in the next class, and thank you very much essentially, and stop here. Thank you.